So when we think about math, we don't necessarily think about everything that math can be. It can be, on one side, very technical, and we tend to think about it in that way. We think about math as being intimidating because of its technical side, which at first glance can be extremely confusing. But it can range from very technical to not technical at all, where it's the thought process behind it that is the key, and a lot of it that you write down will just be in English. The first couple of sections fit in that very much. So the first concept that introduces, that leads us to inductive reasoning is the game of billiards. Now, it's sort of like pool, I guess, but without the pockets. And the positioning of your balls is really a part of the game. It's not really relevant exactly how the game works to us, more the setup. You have this rectangular table, and when you hit a ball, it's going to, of course, bounce off the edge at the same angle that it hit the edge. For example, if you move the red ball along that line, it's going to hit at the same angle and bounce off, and then it might hit a ball and hit other stuff depending on how fast you hit it. So this leads us to a more abstract question based on that. That if I have, let's say, a 5 by 10 rectangle, and I keep it simple, I'm hitting the ball at a 45-degree angle, so all of these angles, the angle that it bounces back is going to be 45 degrees, just to keep it nice and simple. That's always going to be the case. So it goes up, you can follow the path. It makes a diagonal with every little square to just make it easy to track. And it's going to bounce back here on the right side and head straight for the corner. So the rules of our game will be it keeps going forever until it hits a corner perfectly, and then it stops, as if there's a pocket. So in the left one there, it goes, bounces once, and then it hits this top left corner, and that's where it stops. But now I can change the rectangle, the size of the rectangle, the dimensions. Let's say a 6 by 10 rectangle. Which path is the ball going to take then? That has a more interesting path by just increasing this width by 1. Now it goes up diagonally all the way to an edge, and then bounces perfectly back, bounces there, bounce, 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 until it hits that corner. So that tells me that the dimensions of the table, or the rectangle, will determine the path of the ball and where it ends up. So now if you look on the second page, which has no numbers, well, we're going to deal with that. We have a whole bunch of different tables, a whole bunch of different rectangles. So your first task, the first exercise, is to use a ruler, even free-handed if you want to, and see if it always starts at the bottom left. Where is it going to end up? So I have a bunch of examples. You can have many other examples. These are some of them. Hopefully sort of varied, giving me different paths. So let's see, if I start on the bottom left and it bounces until it hits a corner, where does it end up? This is where you get out a pencil, not a pen. Pen's dangerous. Pencil. And use a ruler if you want to, or just freehand, and see where does it end up. So take 5 minutes. I will play a little video that's sort of related to this for those that finish quickly. Take not as long as you want, a couple of minutes to see the path of the ball. Or if you don't have the book yet, make a rectangle and see what the path would roughly be. It doesn't have to be perfect. We just want to start actually doing something. Just sitting back and listening, it's all good, but unless you start actually drawing and writing and doing something, it's not actually sinking in as effectively as it can. Some people are really fast, some people are really slow, some people are in the middle. Doesn't matter at all. I'll play you a little amusing video just for fun while you're working on this. All right, everyone should sort of be done, I would hope. And if you're not, that's okay as well. You don't have to be perfectly done. Let's have a look at what we found. So if we did it carefully and followed the path until it ended up at a corner, then it should look like that. Now I have a whole bunch of different paths. And from these examples, I can start asking questions and draw conclusions. At the bottom on the textbook, the first question, I'm not sure if it overlaps exactly with this, it might. For what table dimensions does the board have the simplest path? I'm going to read it so that you can look at it in case your paths aren't correct. You can listen to the question and look at the examples at the same time. For what table dimensions does the ball have the simplest path? 6 by 6. Why do you think that is? Because if it's a square, it's just going to go diagonally to the opposite corner, and it doesn't have a chance to bounce. Second question. For what table dimensions does the ball travel over every square? 5 by 7. Is there another one? 2 by 3. 3 by 4. 2 by 5. There's a whole bunch of them. What makes it special? And of course, there's no real right or wrong answer because we have a limited number of examples. So there's a little bit of guessing right now. So you can't really be wrong in your answer. What do you see, or what do you think you see that makes those ones special to have a path traveling over every little square?
Odd numbers.
He says odd. Did you say odd numbers? That's a good start, but there's a 2 and a 3. 2's not odd. 3, 4. 4's not odd, so it's a good first guess. But that's not quite it, because there's a 2 and a 4 in the dimensions as well. So I'm not expecting you to have the perfect answer. I'm just starting to see how does this thought process work. I have examples, I ask questions, and I'm trying to draw conclusions about how these things work in general. So it's okay to not have answers for any of these, honestly. We're just asking questions. For what table dimensions does the ball not travel over every square? For many of them. Do we see a link between those? Yeah, 6 and 6, it's the same, but they don't have to be the same, and I could still miss some of the little squares. Have a bigger path or a wider path. Again, we're just asking questions. There's no need for precise answers right now. Can you think of a rule for telling in advance if the ball will travel over every square without actually doing it? What if I have a huge table? I have little examples, and I want to make conclusions in general. What if I have a huge table and it's too time-consuming or tricky to make the path every single time? Can I use these examples to draw a conclusion to say when is it going to travel over every square? Is there anyone that has an idea? There's no real right or wrong. Well, there is a right answer in this one, but it doesn't matter if you find it or not. Yes.
If you were to double something like the 5 by 7 and make it a 10 by 14, would that just double the size of the squares, or would it also run over every one?
That is a good question. It would double everything, double the width, double the height, and you'd have to draw it because there isn't really, oh, there is one, right? 2 by 3 is double to 4 by 6. So the 2 by 3 one travels over every little square, but the doubled one does not. That's a good, or use.
Has to be an even length of sides matched with an odd length of sides?
Even length matched with an odd length. Okay, what about this one? Odd and even. Those are all good observations, very good. And it's part of the process. that you're trying, you think you see something, and there's another example that sort of counters that. Yes?
All the ones that go over every square are in their like lowest fraction.
There we are. It turns out, now we don't have a lot of evidence, so your guess is limited to the evidence that you have, to the examples. In this case, it'll travel over every square if, I can't remember how you said it, if there's no common divisor, let's say, between the length and the width dimension. Because as soon as I double it, now 2 divides into both. And I don't have that anymore. The key here is how we use examples and a limited number, because you don't want to make 100 of these. It's too tedious, time consuming. You have a limited number of examples, and you're trying to make general conclusions from them. Are there more? Number 5, for what sets of table dimensions do you obtain similar paths? Similar paths. That's a trickier one. If you look at the 4 by 10 and the 4 by 6 at the top, they're sort of similar. So we can ask different questions. Similar paths, when am I going to get that? 2 by 6 and 3 by 9, that's maybe a better one. That's a similar path too, but in a different way. That one, if I sort of scale it up, then I can still get a similar path. But the scaling doesn't have to necessarily be a doubling. The 2 by 3, this one, and the 4 by 6, they do have similar paths. Those are better ones. They do have similar paths, though one goes over every square and the other does not, but they are similar. So you can ask different questions, and then different properties of those numbers would give you those. I don't want to take it too far, so you can think about the others if you want to, but they're not test questions or anything like that. The key here is the following. Inductive reasoning is the process of collecting evidence, drawing examples, or going out in the world and collecting evidence, doesn't matter. Noticing patterns in that evidence that you collected, in the examples that you drew, and forming conclusions based, general conclusions about how it works in general. Not just those examples, but you're basing it on these examples. And that's a dangerous game when you think about it. The caveman sits boiling water and he says, it's a little small, he says, water boils down to nothing, snow boils down to nothing, ice boils down to nothing. Conclusion, everything boils down to nothing. That's not a correct conclusion. You just didn't take general enough things. You just took water-based things, and yes, they're going to boil, but not everything does. So you have to be careful what your evidence, what your collection of pieces of evidence is, and it has to be enough to lead you to correct conclusions. I want to just, before I do this one, insert one that's in the textbook that I don't have a slide for. I zoom in. This one, if, for example, laptop is so slow. If, for example, you looked at all the tables with varying width but the same length, 8, for example. You looked at 1 by 8, 2 by 8, 3 by 8, 4 by 8, and so on. For every one of those, the path ends in the top left corner. Are those examples sufficient to conclude that regardless of the board, any board, the ball is going to end in the top left corner? That's the conclusion you can base on your example. But that's not a correct conclusion in general, because I didn't vary my examples enough. I don't have enough examples. As we saw in the previous one, there are many that will not end in the top left corner. So you're limited by your examples, and you're basing your conclusions on that. And that's a little bit of a risky game if you don't have enough conclusions. There's a story in the book that I'll just tell in my own words. You have a scientist, and he's working with fleas, and he has a jar full of fleas, and he takes one out, and he shouts, "Jump!" and the flea jumps. He does it again and again, and every time he shouts, "Jump!" the fleas jump. Then he switches the experiment a little bit. He takes out a flea, he pulls off its hind legs, puts it on the table, shouts, "Jump!" and the flea doesn't jump. He does it again, pulls off the hind legs, put it on the table and shout. Doesn't jump. So in the end, he draws the conclusion that fleas with their hind legs pulled off are dead. That's not correct. So inductive reasoning, though a very common scientific way of reasoning, has its risks, its limitations, that you're basing your conclusion on what you observe. Yes, if the apple falls enough times from the tree, your conclusion about gravity is correct, but it is also dangerous to use inductive reasoning. Next page, exercise 1.3. You can easily draw this yourself. Let me just zoom in a touch to get to the top one. So let's look at this. Because this is our first introduction, we are not always going to go right to the end, 11:20. If anyone feels, I'm paying good money for this course, I want to go to 11:20 every day, please let me know. I'm sure I can give you something. But we're still getting into it, right? Still getting into the swing of things. Inductive reasoning is mathematical thinking. There are no variables. There are no equations. Doesn't mean it's not math. Math is a way of thinking. Let's look at this. So I have circles, and I first put 2 dots on the circle, and then connect those dots with a line, and that breaks the circle up into 2 regions. Then I increase the number of dots to 3 dots, making a little triangle, and that's all the possible lines between pairs of dots. And I break up the circle into 4 different regions. Then I increase the number of dots again to 4, and you connect all possible dots. Any 2 dots have a line between them. And that breaks up the circle into 8 different regions. You want to increase the number of regions. Only 2 lines can intersect. See here, only 2 lines can intersect. That's important when I get to more dots. Now your task is make a circle with 5 dots. What is the largest number of regions that it breaks the circle up into? Oh, you have to give people a chance. So we have dots or points. 2, 3, 4, 5, 6. And the regions. 2, 4, 8. And we have to find the other ones. We're collecting evidence about the number of regions based on the number of points on the circle. So take your time, do it freehand, do it however you want to do it. Make 5 dots on the circle and see how many regions does it break the circle into. Just because he says 16 doesn't mean it is 16. He could be messing with you. So you want to confirm it for yourself. Can anyone else confirm 16 regions? All right, so 16 looks good. So now let's pause here. 16 is correct. If you're looking at the pattern of numbers of regions. And you stop there. I'm tired of drawing circles, I'm tired of making lines, I'm stopping there and I'm making my conclusion now. 2, 4, 8, 16, 32. So, continuing the pattern, it looks like when I draw 6 points on the circle, it'll break the circle up into 32 regions based on the evidence that I have. Just make sure that you don't have 3 lines crossing in a single point, then you're missing a region. There have to be as many regions as you can. So only 2 lines can cross. Now, fair enough, that circle's a little small, so you're going to have to really be careful with your 6 dots. The number of regions the number does increase quite quickly. We're trying to confirm. I think it's 32 based on what I've seen so far. Is it actually 32? It is in fact 31. And no matter how hard you try, it will not be 32. If you do it correctly, carefully, it will not be 32. It just isn't. You want it to be, it just isn't. And that's the, I guess, good and bad thing. The bad thing is, well, if this isn't 32, that throws my conclusion completely out the window. And the pattern that's happening here is actually much more complicated. A little bit too much for us. The good thing is as well that science and mathematics doesn't depend on my feeling at all. I can want it to be anything. It is what it is. There is no feeling or emotion behind it. It is what it is. If I stop too fast, inductive reasoning can lead me to the wrong conclusion. That is the single point I'm trying to make today. It is a good form of reasoning, a necessary form of reasoning, but it's based on the evidence that I have, and if that evidence is too limited or too one-sided, it could lead me to the wrong general conclusions. That is it for today. Any questions? I know if you have objections, I can probably ramble on for another 15 minutes, but we don't want to start too fast, freak people out. Nice and slow and steady.
If all the points were like geometrically the same distance from each other around the
Then I'm going to have multiple lines intersect at the same, and I'm going to lose regions. In this case, it's going to be a 30, yes. And that's another thing you could say. If they're all spread out evenly, what are the numbers then? But then I get 2, 4, 8, 16, 30. That's also not a nice pattern.